So now I think we should look at, well, let me see. We could look at some exercises, but I don't have any handy right here. Let's do the last topic, and then we'll do exercises for the rest of the time. The last topic, I think, in conditional probability is the principle of total probability. Okay, so here's the idea. Let's say that here's your sample space. And let's say we can divide this sample space size, this sample space up into a series of events that don't intersect. Here I'm just going to draw 4. So we can see that S equals E1 union E2 union E3 union E4, and the intersection of any pair is equal to the empty set. So I check where I and J are equal to 1 up to 1. I take any, this notation just means pick any 2 of these and their intersection is 0. So this is called a partition. So a partition of S is sort of a division. It's like a division into separate domains. Oh, so for example, in terms of the area of the United States, say, you could say that the states are a partition of the area of the United States because they fill out and there's no overlap. Every point is either in one state or the other, presumably. Okay, now let's look at what might be the case. Let me draw this partition again. Here's S, E1, E2, E3, E4. Okay, well now let's say here's event A, and let's say that we're interested in the probability of A. Well, this is a complete probability. So we're interested in a total probability. Total, that's where the word total probability of A, which is just our normal probability, but we're going to phrase it in terms of dividing it up into pieces and using conditional probabilities. The idea is maybe it's hard to calculate A, but maybe it's going to be easier to divide it up into pieces. Well, let's look at, it turns out that A is going to equal A intersection S, right? Because this A here, because A is a subset of S, the intersection of A and S is just A, but this allows us to use this division. This is S is equal to E1 union E2 union E3 union E4. There's nothing special about 4. This is just a sort of big concrete, the general case. Well, there's some set rules. Remember, we can distribute this intersection in. This is going to be A intersection E1 union A intersection E2 union A intersection E3 union A intersection E4. And you can see that because basically A is going to be this piece plus that piece plus this piece, and the last one here is going to be the null set. So basically it's just saying the area, the elements of A can be divided up into those parts of A that are in E1, those parts of A that are in E2, and those parts of A that are in E3, and those parts of A if there are any in E4. Okay, now it's crucial that the intersection of these sets, because this is a subset of E1, this is a subset of E2, there's no overlap, there's no intersection between these sets. So we can write A we can write A equals, well, I'm just repeating this, but you can say that the number of elements in A is going to be the number of elements in here plus, because there's no overlap, plus this should be intersection E2 plus A intersection E3 plus A intersection E4. Okay, well, so then if we want to know the probability of A, well, that's going to be this whole thing divided by S, probability of A plus the probability of A intersection E2. I mean, not the probability, plus the number of elements in the intersection of A and E3 plus the number in the intersection of A and E4. And that all divided by number of elements in S. Now I can write that out. I can sort of multiply this into each time, to sort of take out the numerator, then multiply in 1 over S to each term. That's going to give me, I'm trying to make plausible a result. You just have to follow this and sort of see that it makes sense, hopefully, to what is going on. And it works for any number, for the partition to be any size. Well, this is sort of the take-home piece here, because this total probability, because you notice this is almost, it's got the piece that's like the definition of a conditional probability, except if this was a conditional probability, we'd have to have the number of elements in E1 in the denominator. So we can write this as sort of multiplying and dividing by this. Okay, see, I multiplied numerator and denominator by the number in E1, by the number of elements in event E1, then sort of divided up the fractions. So if I multiplied these two together, the E1s would cancel and I get this first one. So I can do that for each one of these. And maybe I should have just used 3 here, but maybe that slows everything down a little bit. Plus E4 over E4, number of outcomes in E4. Okay, now let's look at what this is, the probability that of A. We're deriving or finding the law of total probability. Now here, this now is the probability of A given E1. This piece is just the probability of E1. This is the probability of A given E2 times the probability of E2 plus the probability of A given E3 times the probability of E3 plus the probability of A given E4 times the probability of E4. Okay, well, that's the law of total probability. It just says, it's a relationship that says, why would you want to have this law in the first place? What use is it? Well, it's useful when when each of these pieces is easy to calculate. The partition presumably makes it easy to count P1, probability of E1, E2, E3, E4. And then if the conditional probabilities are somehow easy to calculate, then this makes the calculation of this easier. So the problem is that we want to look at the examples to understand how this works. There's an example here, and you can read about. Maybe we should do that. Maybe we should go through something like this just so we can, this seems concrete rather than abstract. But that's the derivation of the